Hello and good day to you. So today I'm going to try and go through covariance and linear regression. What I'm trying to do is show you why covariance is a bad thing. I'm not really building a very functional model out of this. I'm just trying to show you how to detect problems in your own model, how to sort of maybe investigate and look into it. So what you can think about with covariance is when you're making a general linear model using the ordinary least squares method of calculating how much one value affects your model, how much it puts into your model. So if you remember the algebra we talked through in previous videos, but the idea here is that if you have multiple values which are roughly the same or correlated, you're going to inflate the errors within your calculations, because when the ordinary least squares model tries and runs through it, it's going to not be able to tell the difference between these values, and it will inflate and change the data. Now, if we're saying that, one thing to think about is there's a couple of ways covariance could come about, and then move that into your thinking. So I in my head have three ways that I think that covariance routinely come about. One is you've got two values, say number of weeks and number of days, and those are really basically they're both the same thing of time. And those two objects, if you had in your data, would become covariance because they're the same. The other is if you have a value in your data, and let's say you're doing some linear regression and you've got rainy days and you've got holidays, but you always go on holiday in rainy days because you're just really unlucky. Maybe you're the rain god in the Hitchhiker's Guide to the Galaxy. Now, if that's happened, those two values are going to be treated as if they are joined at the hip and the same thing, and they are going to do the same and balloon out the estimate of that the ordinary least squares gives to those two values. And the third way this could happen is, let's say you've got a variable, and if, say, you've got Friday in your model as a binary 0 or 1 for whether it is Friday or not, that Friday becomes fully covariant with anything that sort of happens on Friday. And if that's a general trend, then it might become inflated because of things that happen on Friday, and it can become even more inflated if the other days of the week you have additional values that let the ordinary least squares kind of pick apart not only the day Friday, but some of the things that happened on that day, so to speak. So those are ways where you can end up with covariance. That's just a short explanation on my part. But the idea being is this: when that happens, you're going to have increases in your data. If you want to follow along, you need to load the libraries caret, Charlie Alpha Romeo Echo Tango, and car Charlie Alpha Romeo. You're going to need to exclude any. You just want numbers, so you want to exclude stuff like customer ID. I'm using credit card general information from Kaggle if you want to search and follow. You do, like a lot of our functions, need to omit NAs. In real world, you need to investigate your NAs and find out why you got why they're NAs or why they're blanks. That's always good practice. But you use from caret the fine linear combos, and what it'll do, there isn't any in it, I have to say. It'll give you a list of variables to remove if their correlation with each other is between 0.7 and 1 or minus 0.7 and minus 1. If it finds, it will give you a list to remove. Hopefully that lets you clean up your model. So there is one methodology of, and I'll go through methodologies hopefully of doing a linear regression later. But one methodology is to put everything in with the kitchen sink and then find the correlations and pull them out. Another way to check that you don't have any problems, any covariance going on, and this is basically you're doing part of the matrix calculations that R does, and if you were to get a 0 there, that means that so when covariance gets to 100%, it's probably just going to ruin the model. In fact, the calculation just might not work, or probably doesn't work because it's using a matrix. I've not gone into my matrix calculations far enough to, explain that in a very succinct manner at this point, so don't ask me. But I'm going to create a linear regression for data purchases. I'm using everything to show you the problems you can have. Now, I do have to stress I'm not trying to build a perfect model. I'm trying to show you issues that you can have and how you make a better general linear model. And to show you that, you can see my multiple R squared and adjusted R squared are 1, which basically means it's as good as guessing the average. So this isn't much a better model than a basic guess. If for everything if it is below 1, it's better, and increasing as it is lower. But you've got your intercept and the variables. What you then want to do is, if you think about it like this, if you use the car library, you can put your result value in. What you get this VIF function from the car library, and what VIF does is it stands for variance inflation frequency, I think, and that's completely off the top of my head. But this is a comparison between if you just did a linear regression with that one value, and you did a linear regression in a full value, what is the inflation being caused for that value? And if you look for big numbers, like you can see here, data purchases frequency, purchase installments frequency, something is causing those values to increase. So you've got a 10 and an 8, there's a good chance of considering dropping one of those values to reduce the covariance going on. So let's actually do that. I hadn't thought about doing that in the prep for this. So what we're going to do, I'm going to drop purchase frequency regression summary. That's me moving the mouse too quick. So have we got a better model? Well, the R squared hasn't gone down. But if it hasn't gone up, then you can say that it probably wasn't needed. So have a look at the VIF again. You can see that's a lot better. The other one isn't inflated by an 8, so there probably was some covariance going on there. It's good for something to drop out. Now, it's probably a case that there's so many random things going on that you can't really predict purchases from things like balance frequency and one-off purchases and the like. Again. But then having a look at your data, the final thing that you can do is, if you use and I'm not going to show you to do this because I've installed too many packages for R today, but you can use the function glht to do a hypothesis test on a general linear model to see whether what you got out of it was just random. And the idea being is these estimate values, you can start looking around and seeing, you can see that installment purchases has the biggest correlation there, the biggest coefficient. That's really high. Oh no, did I say that wrong? Oh, it's got a minus. I think it is, isn't it? Okay, no. One-off purchases has got the largest, just by a very slight amount. But then looking at that, you can sort of almost try and look and create it. Does all the others add up to the same effect as this? Is this your biggest cause, and you can go away and create a hypothesis from this? So I hope that was a little bit tantalizing. I hope that means you go away and think that you could do something more with a general linear model. I hope that's good enough. Have a good night and a good day. Bye.